As we focus on problem solving with density, we don't want to forget the big idea. Density is a physical property. Every substance has its own density, and density can be used to identify a substance. If you were in industry and you were buying a large quantity of pure copper, and you took a sample of that copper and it checked the density of it, if it doesn't have the density that matches the density of copper, then they're not selling you pure copper. It's something else. You need to investigate that, right? So we want to just kind of remember that it is a physical property. It's something we can use to identify a substance with checking its density. As we also go through our work with problem solving, we want to be very quick to recognize units, recognize that mass is in grams, recognize units of volume as milliliter or centimeter cubed, and recognize those density units. Today we're talking about graphing. We did some graphs earlier this year and talked about how we always put the independent variable on the x-axis and the dependent variable on the y-axis. This is a good time to review that piece of information. When we're graphing, we use different kinds of graphs for different purposes, and sometimes when we graph data we connect all the dots because we want to see how that data flows. We want to see the change in the data and how it changes over time. But other times we take our data points and we draw what's called a best fit line. And here's an example of a best fit line that has a lot of points on our graph, and then there's one trend that we're looking for, and they just drew the line of best fit through the middle of that trend. When we draw a best fit line, if we have a graph and many of the points can fit on that line and make a nice straight line, that's what we want to see. We want to pick up as many of the points as possible, but those data points that aren't on the line, we want to draw our line of best fit in such a way that those points that are off the line are equally distributed above or below the line. And here's a really good example of that. This is a density graph. You can see that the y-axis is mass and the x-axis is volume. Each of these points on the graph represents a sample of a substance. So there was a substance and they were measuring the mass of each sample and the volume of each sample, and each xy coordinate point is one sample in the data that they gathered on that sample. We always include 0, 0 as a coordinate point with density because think about it, if you have 0 mass, you have 0 volume. If you have 0 volume, you have 0 mass. So 0, 0 is always a valid point on a density graph. And so density graph lines always go through the origin. You're never going to have a line that's a density graph that doesn't go through 0, 0, the origin. So you can see that they drew this in such a way that most of the points are right there on our line, but those that are not are relatively equally distributed above and below the line. That is called the line of best fit. And that helps us to get the trend that our data is giving us and understand that those errors are going to be there. And if you have a normal situation with research, the errors in your data are most likely going to be equally distributed, a little bit above and a little bit below. So we're always going to want a straight line, and when we have a density graph, the slope of the density graph is the density. So we've talked about slope probably in math class, and slope is rise over run, which is, here's our rise, here's our rise, here's our run. So the slope is the y over the x, and if we have mass, on our y, and we have volume plotted on our x, then the slope is mass over volume. That's density. Density is mass over volume. So the slope of a density graph is the density. That's why we call it a density graph. And here's an example. And you can see that they're calculating the slope. They're taking two coordinate points, and they're taking we use the Greek symbol delta in math. It's a triangle. It's a Greek letter delta. And in science, when we see that delta, it means the change. So we're looking at the change in the y value between the two y points and the change in the x is our denominator. Okay, so you can see here they got their two coordinate points, and they're doing the y minus y over x minus x and coming up with a density. So you should have the graph that's labeled graph number 1. That's the easy intro graph. And reminders, you always label the x and the y axis. If the graph doesn't have the numbers in it, then you have to choose what interval you're going to count by looking at the data and analyzing the graph with the data that you have and deciding, do you want to count by 2s or 5s or 10s, etc. Here's your graph that you're doing. You can see that the coordinate points are up there in a data table because that's what each point is. It's an example of this liquid, and they had 1, 2, 3, 4, 5 samples of the liquid. For each sample, they measured the mass, they measured the volume. And so this becomes XY coordinate points. Now, this shows the mass first, and quite often you're used to seeing X, comma, Y, right? When you see coordinate points. So you could rewrite them. 4 is your X value, and it's getting paired with 20. There's your first coordinate point. And then 20 is getting paired with 100. Okay, so go ahead and graph your points. Here's 4. You're going to find 20, and there's your point. And then the next one, we have an x value of 20 with 100, and there's your point. Get your point put in. So go ahead and graph those points. You can pause the video, graph them right now. Then when you get your points put in, draw your line and make sure your line goes through the origin. Include the origin in your line. Now we can answer some questions. I'm going to let you answer numbers 1 and 2. As the mass increases, what happens to the volume? Does it increase? Does it decrease? Does it stay the same? Those are your possible answers here. Does it increase? Does it decrease? Or does it stay the same? How many grams would occupy 12 mil? Well, they're giving you an x coordinate, and they want you to tell what the y coordinate is. So find 12 mil. Go ahead and find its location, 12, on your line, and then back that out and read the y value. You have 60. That's mass. Keep your units in there, 60 grams. Okay. What volume would 90 grams occupy? Well, go ahead and get your 90 grams, find your line, read the y value. And then the next part is what is the density? Let's look at that. And we're going to use this formula. I did have it formatted with subscripts. You're used to probably seeing it with subscripts, but sometimes when I use this program for writing on slides and taping it, I lose formatting. Okay. So what we're going to do is we're going to select 2 points. Okay, and we're going to take y2 minus y1 and put it over x2 minus x1, and we're going to calculate our density. So here, it doesn't really matter what you choose. Ideally, you choose two places that aren't your data points, but we can choose data points, that's fine. You want to select 2 points. So we want 2 x, y coordinate points. I'm going to go ahead and take 4 and 20, and then I'm going to take, we got 15 and 75. Just kind of picking randomly here. Those are my 2 xy coordinate points. So I want y2 minus y1 over x2 minus x1. So these are my 2 y's. Okay. $75 minus 20. And then I've got 15 minus 4. Go ahead and use your calculator to do the division. Our density is 5. And we always want to include our units. So we have y over x. So this is in units of grams per centimeter cubed. I'm going to run out of space here. Okay, so that's our density. Okay, go ahead and take the graph number 2, and that's the next one you're going to do. And this time you're going to be able to label your axis, set up your axis. We're doing a density graph. Again, mass is always on the y. And then volume is going to be the x. And so what we're looking at here is you're looking at kind of a y-x in your chart, and some students want to see it look like xy coordinate points, and you can go ahead and recopy that if you'd like to. Axis, and then take a look at your numbers and decide how do you want to count. And I think I have. Then of course you're going to label your on this graph. The decision was made to count by 1s on the x-axis and by 10s on the y-axis. That shows that, yeah. You can go ahead and make a list if you want to. Just keep in mind that you have your y coordinates first and then your x coordinates here in the data table. If you need to see x, y coordinates that look the way they do in an algebra book, you're going to have to recopy them. Okay. So now you're going to go ahead and start plotting those points. You have what, 10 or so? 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, 10 points you're going to have on your graph. Also, on your data table, go ahead and pick up a calculator and just divide to get the density, the straight density for each of the samples. Again, each of these set of coordinate points was a sample that they measured in the lab. They measured the mass and the volume. Go ahead and take the mass and divide by the volume and fill in a density for each of the samples on the data table. Here's how the first points should look. I'm going to go ahead and let you finish that. Once you get all your points in, make sure you draw a line that is going to go through the origin. Okay, it's going to look something like this. I didn't draw the line. I'm going to let you do that. And then choose 2 of your points and calculate the slope. And once you get your slope, that's going to give you the density of the substance, and then answer the question on the back of the paper about identifying what that substance is.